And as you have seen earlier this day, so the power virtualization can be divided into types. Type 1 is the hardware and the virtual machine monitor, and nothing can skip the virtual machine monitors. All the operating systems are running on top of the virtual machine monitor. While at the type 2 hypervisor, you may have software running directly on the host operating system. And also the virtual machine monitor itself is running as an application within the host operating system. And then virtualized operating systems are running on top of the virtual machine monitor. Then what is partitioning? It's some kind of custom-made virtualization. Looks like this. So we have different subsystems. Every subsystem contains its own operating system, and every subsystem, so each partition contains its own subsystem, can be used independently of the others. And the resource allocation is done by custom firmware, so on the hardware side. And this is a technology which is, for example, used in IBM mainframes. There are also more recent architectures where only the CPU and not the entire system needs to be partitioned, and the partitions may share the RAM. So this is basically something which is used for very special custom applications. It's not standard hardware you could buy somewhere. It's usually the hardware built for a specific purpose, and also it's firmware built specifically for this purpose, and only works with special hardware. So it's fairly exotic partitioning concept actually, virtualization concept. Then we have emulation. This is maybe something we have already played around with. So emulation completely simulates the hardware, not any hardware, but always a specific hardware, the hardware which is emulated. And thereby you can run the original operating system. So you can run the unmodified operating system. But be aware that emulation is not equal to virtualization. So it's actually more than that. Because we are now here, we are emulating an entire physical hardware. So you can actually, by using emulation, you can really run any type of software built for any architecture, because it's not dependent on a specific instruction set, because the instruction set is emulated as well, so the entire CPU is emulated. Examples for this are QEMU or DOSBox or Box or WinUAE. WinUAE is Amiga emulator, it's an old computer system. DOSBox is for all DOS applications. And Box is more generic for different PCs. It's required to run code for other CPU architectures because virtualization usually means that the code is still there's a pass-through of the code to your CPU, but the code itself is not changed. And emulation is different because it actually translates the code into different code. So it translates the code of the target architecture into code for your own CPU architecture. And therefore, you're actually able to run code which is compiled for different CPU architecture. For example, there was an old architecture called Motorola MC68,000 something. And this can then be emulated on the x86 architecture. For example, the first Apple Macintosh computers used this kind of CPU, also Atari and Amiga, and some others as well. The advantage is, of course, that you are able to run the original software, which is quite nice, because very often for historic architectures, the hardware is unavailable, or because it may age, so everything which is physical in our world will age and finally be safe. So software is immaterial, so you can use emulation to actually execute software even if the hardware is not physically available anymore. But of course, it comes with a cost, as always, so the disadvantage is it's very, very inefficient. It's very inefficient, so you're losing orders of magnitude of performance by using to use emulation. Well, there's an example like this. There's actually a JavaScript emulator. I will show it to you here. You see, you can, I'm not sure how this works, but yeah, you see you can run this game. Yeah, I'm not sure how it works, but yeah, I mean, you get the idea, right? So this is actually an emulator for the Nintendo Entertainment System. So from the, I guess it was somewhere from the 80s, 1986 or something. And yeah, the interesting thing is here that the emulation is completely, entirely implemented as JavaScript. So the entire emulation runs within your browser as JavaScript. So yeah, actually it's really possible to emulate a complete hardware architecture in JavaScript. So yeah, very nice example. And yeah, as you can see here in the diagram, so we have hardware, then we have the host operating system, for example Windows. Then we have the emulator. This is basically just an application running on your host operating system. And then the emulator is, on top of the emulator, we have emulated hardware. So the emulated hardware is actually completely simulated by the emulator. And then we have the original operating system, which runs on the emulated hardware, but it's not aware that it's emulated, because everything feels, from the point of view of the software, everything feels like the original hardware. So we can run the unmodified original operating system, and of course, on top of it, the original applications run on the original operating system, which runs on the emulated hardware, which runs on the emulator, which runs on the host operating system. So yeah, it's a long way down the stack. That's why it's actually also, as I said, it's not very performant, it's very inefficient. But it works, as you can see. I mean, Nintendo Entertainment System is, I guess it's one of these 8-bit architectures, so it's not that you would actually need high performance for that. So even if you're losing orders of magnitude of performance, it doesn't pose a problem here, because our PC is so much faster than the system, a million times faster than that's not a problem at all. But of course, it may be a problem if you would want to emulate current PC architectures, for example. Yeah, speaking of PC emulation, you can also emulate a complete PC. And this even works in JavaScript. Yeah, I can also show you this. So this is actually, sorry. So for example, I want to run Windows 2000. So here the PC is booting. So it's not fake, it's a PC, it's booting. So we have the emulation of the BIOS, we have the emulation of the entire PC hardware, including everything, not only the CPU, but the main one, all the stuff. Everything implemented in JavaScript. And now we see that our virtual emulation, it's not virtual, it's an emulated PC, it's starting Windows 2000. Yeah, it's pretty old software, but we get the idea. So you see, we can now it's running and starting up. And yeah, I mean, it's an emulated PC, so it's supposed to be very, very slow. That's why it runs this very old hardware, very old software here. It would be terribly slow with current software currently. But you can see we now have the PC up and running, and I can even move for some kind of interaction with my emulated PC. So this is yeah, a fully featured JavaScript PC. Yeah, I guess we can also. That's my start menu. Yeah, I mean, if you look at the device manager, you also see that all components of the computer are being emulated. Yeah, it's not fast. Yeah. But still, it's, you see here that we have disk drives and display adapters, so it also emulates a graphics card along with the BIOS of the graphics card, emulates a floppy disk controller, it emulates an IDE controller, a keyboard, mice, monitors, network adapters, also a soap card, and other stuff. You see, so all of this in JavaScript. So it's, I still find it quite impressive to, I mean, it's basically more a technical challenge, but still, I find it quite interesting that someone is actually able to implement something in JavaScript. Okay, so even a complete PC can be emulated in the browser using JavaScript. But as I said, emulation is very, very slow. So it was like 25-year-old system, and still it's behaving slower than the original one. So we need something faster, something as application rationalization. So what is application rationalization? Applications run within a virtual environment, and then this virtual environment exists for various operating systems. The most well-known example would probably be the Java virtual machine. But there are others, like for example the Microsoft Common Language Runtime. So it's pretty much the same concept, except they don't call this code, intermediate code which is being created, they call it IL code, I guess, but it's the same concept. And well, the JVM runs Java bytecode, and Java bytecode is generated out of the source code via compilation. So typically we have our source file, and then we have the Java compiler, which creates a class file, and this class file contains bytecode. So the bytecode is still not, can still not directly be executed on any existing hardware, only on the virtual hardware. And then if you run it with the Java environment, then the JVM will actually translate the bytecode into machine code. And the machine code can actually be executed by our machine. And of course, if we are running a JVM on a smartphone, for example, it could be a different architecture, so a different machine code like ARM, not x86, but can be generated out of the same Java code. So this makes it very flexible and also independent of the platform. Also, more recent Java environments have a feature called just-in-time compilation. The idea is that at least for repeated code sequences, the so-called hotspots, the JVM is able to identify these regions and then specifically compile them ahead of time, so that you don't need repeated compilation. If you really have just plain outright interpretation, then it would be slow. So we have just-in-time compilation, and there are basically two options of just-in-time compilation. You could either simply compile everything, but then you have a larger latency in running an application because everything must be compiled beforehand. Or you could just compile those regions of the code ahead which seem to be executed in a repeated manner. And these are, of course, usually the cases where you actually have a speed up of compilation. So it's actually quite a clever idea to specifically compile the repeated code sequences. That's why just-in-time compilers nowadays usually exist. Yeah, then there's another virtualization concept called hardware virtualization, which actually works by imposing virtualization extensions. And these enable using unmodified operating systems. Why is this an advantage? Well, there conventional virtualization without hardware virtualization support has the problem that everything is executed on the outer ring. So this ring architecture is kind of access level on the CPU level. And the ring 3 has the problem that you have a large number of context switches. If your entire system is running on ring 3, then you have more context switch multiplied on the IIA64 architecture. And that's why actually the hardware vendors like Intel and also AMD introduced a feature for hardware virtualization. For Intel this is called DDX and AMD called it AMD, but it's the same idea. Even though it's uncomplicated, but it's the same idea. This must be specifically supported by the virtualization software, which of course is usually the case nowadays. So for example, VirtualBox uses Office, if the hardware supports it, of course. It works by introducing a new ring, the ring -1, and this is reserved for the hypervisor. And this hypervisor has more rights, higher privileges than the virtual machines themselves, and thus we have less context switching required and are able to efficiently execute virtual machines. So the VM kernel itself doesn't need to be run on ring 3, but can run on ring -1. Then containerization. This is actually a very lightweight approach. So it is virtualization on the operating system level. And basically every container is run within an isolated runtime environment. So applications are isolated from each other. But all applications use the very same operating system, as you can see here. So we have our hardware, we have one host operating system, there's only one OS, no more OSs. And then all containers run on top of the same operating system. That makes it actually very efficient, because we don't need to, we haven't all the overhead involved with operating an entire operating system on top of operating system. And the idea is that, even though the applications all use the same operating system, they are isolated from each other. So they can only see applications within the same virtual environment. Of course, usually within one container you have more than one application running. I mean, there is the main application, but of course everything else which makes the application work, like services and tools, whatever. And you have very low performance impairment because of this, and also improved security and stability. The isolation works, for example, by using file system virtualization. So they don't get the real file system, but they get a virtualized file system, which is actually just somewhere down the tree of the real file system. And also process isolation, so they don't see the entire process space, they only see the processes running in the same container. So the operating system calls are filtered by the container engine. For example, if you are within a container and you are requesting the operating system before you're all running processes, then the container environment will take care of the fact that you will only get the processes in the new container, and the others. So the others are filtered out. The same goes for files. As I said, you have virtualized file system. So in the end, finally, the idea is that the application is not able to see anything else except its own container. And this works surprisingly well. And it really, the nice thing about it is, as I said, we have one operating system, low performance impairment, and also a simple deployment process, because you can simply deploy the containers to the container runtime environment. And also it's easy for packaging, and also easy for deployment to other target systems, because you have a defined environment. You have no external factors impairing your runtime. If you would run the application natively on the host operating system, there may be side effects of other applications interfering with the application. This can be very hard to maintain actually. And so you may have problems ensuring that your application runs on all the different target environments. So containers also offer a way to tailor an environment specifically for the needs and to create a very well-defined environment. So that you can guarantee that only what you think must be there should be there, nothing else. So nothing interfering with the application. But the most well-known application for containerization is Docker. Docker has so-called Docker containers, which allow for package assembly, also the distribution or installation, and the execution of software. Docker can be run on different operating systems. So there are implementations for Linux, for Windows, for macOS, and also for some others. And also it runs on cloud platforms. So, for example, Microsoft Azure or AWS, you can deploy Docker containers. So essentially, it's a lightweight virtual machine. The processes are mutually isolated. The hardware is not emulated. So your software runs on the same hardware. And the Docker containers are created out of Docker images. So, what is a container? Container is something which is created of an image. An image is kind of, you could consider an image kind of a class, and container an instance of the class. So the instance of the container, the instance of the Docker image can be created as a container, and you can run the container. And you can create new containers out of the same image, of course. This is the container lifecycle of Docker. So, we start here, as always, backup. And the container is run. I mean, at first it's created, but then we start it's running. And if it's running, it can be paused, and then of course it can be unpaused. You can also stop it. If it's stopped, then it's not doing anything anymore, but you can start it again and it will come back to the running state. Unless you delete it, because then it's deleted and nothing will anymore because you have deleted it. Of course, you can also delete it right from the creation state without actually running it. You can also run it just like around the file system. So not only immediately after creation. This here. So pretty simple. And the idea is that if you want to pause the system without terminating it, you can always just freeze the container, just like you could freeze a virtual machine. Then it will stop doing anything unless you unfreeze it, and it will continue doing what it's doing before. And you can stop it. What are the advantages of virtualization solutions in general? Of course, we have simpler maintenance and management. It's usually offers better hardware utilization. Simply because we are able to put more load on our hardware. Because it can run many applications in parallel, each with their own software stack and their own configuration environment on the same physical hardware. Actually, all software running in cloud systems is usually virtualized in some. There's basically no unvirtualized solutions available as a cloud service. Because you always need this kind of interaction to efficiently manage resources. So we have a better hardware utilization. We have an easier deployment process. We have a better scaling. Higher security also by isolation, which of course is important for cloud providers. It's easier to back up complete ready-to-run systems because we don't have any unknown possible side effects. You can just provision and configure a ready-to-run system and deliver it to the customer, and can be run within a well-defined environment with no other software interfering. It's also easier to create test environments for this. And yeah, it may support historical hardware, even if it's not physically available anymore. So there are lots of advantages of virtualization solutions. But of course, there are also some disadvantages, as always. Well, the most important disadvantage, of course, is the performance impairment, which heavily depends on the virtualization solution. As I said, emulation is worse by far. You have limited availability. For example, software which has copy protection dongles may not work with virtualization. The patching of vulnerabilities in containerized software can actually be troublesome. This is actually a very important point. So, because nowadays, if you have patched a security breach on a single machine, you haven't patched it in the containers, right? So if there are several containers running on the machine, you have to patch it in every container as well. And, if you don't, then every container image needs to be patched separately because it has its own software stack and its own version of the software, and it's independent of the software which might be deployed to the operating system. So you have to be careful and you need to track that, because otherwise a vulnerability may be patched on your host operating system but not on your container. And in this case, it won't be fixed in the software running in the container. You have higher overall complexity. This is also always a disadvantage. You should never increase complexity without a good reason, because the more complexity you have, the more complicated it becomes. It's always the case. So more complexity means there are more options, something can go wrong. And also it means that it's more difficult to understand what's going on in general. This really holds for everything. So of course virtualization somehow makes things more complicated. So you need to have a good reason for this, but of course we do have. It's not suitable for applications which require direct hardware access. And also for those which require low or deterministic latencies. This is the case, for example, for real-time applications or instrumentation and control applications. There are approaches which try to fix this a little. But of course, yeah, the deeper your stack is, the more troublesome it becomes to guarantee some kind of latencies, because you don't have control over what the host operating system does and how long it takes to do something. So usually it's not suitable for real-time applications. So we should never use virtualization for something like a flight level control system in an airplane or something. Be a very, very bad idea. So everywhere where you actually need direct hardware access and you need to understand what's going on the lowest level, which is actually directly working on the hardware, needs to exploit certain properties of the hardware. This is not suitable for virtualization. Also, it can create new attack vectors, because the isolation can actually sometimes be penetrated, for example, by timing attacks, as I said earlier this day. So, consider this before deciding in favor of virtualization. To sum it up, hardware virtualization is often used by cloud providers, such as AWS, used for custom operating system. The full virtualization enables using unmodified operating system. Partitioning is very special crafted hardware, and also fitting firmware, and it's only used in special cases. One example for this is cloud gaming platforms, because cloud gaming platforms require low latency handling. Because for cloud gaming, low latencies are very critical. So otherwise, you will miss everything because the transfer is too slow. So this is why sometimes this is implemented by hardware partitioning, so special solutions. Hardware emulation can be done, can be used to run historical software. Very high performance code, often used for all game consoles, home computer systems. As you have seen, now even can be run in the browser, no problem. And the application virtualization is the basis for managed languages, such as Java and C#. So C# is actually just one of the languages you can run on top of the common language runtime from Microsoft. There are some others. For example, there is also a functional language called F#, which are able to prevent invalid memory access. This is an important aspect of languages like Java, that they are monitoring memory, so you cannot really corrupt the memory. So it makes the languages very safe because the application cannot crash because of this. The hardware virtualization allows for running unmodified host operating systems efficiently by introducing the string -1. And finally, the containerization, which very often it's done by Docker. Not always, there are others, of course. It's a lightweight form of virtualization, which usually isolates applications running on the same operating system, and it's the preferred basis for many cloud services. Okay, so much about virtualization concepts. Now let's take a deep dive into AWS. What is AWS? Basically, it's a collection of a large number of cloud services. And by large number, I mean like something 80 or 100, I don't know, I haven't counted them, and it's oscillating very, very many. And it's also not a good idea to learn them by heart because they may change tomorrow. So lots of cloud services. But there are some very important ones which are also being maintained for a long time. The Elastic Block Store, and also the simple storage service, services for storage, for data storage. Then there is the Elastic Computing Cloud, which allows the creation and the running of virtual machines. Then we have the Elastic MapReduce service, which is, as I said, it's an orchestration platform for creating and running a cluster on EC2 instances. And we have AWS Lambda as a serverless computing service. But as always, there are many more services for authentication, for databases. We also have the Redshift database, and so many more services. But these are certainly for our applications and for cluster computing. These are by far the most important ones. So what is the EC2 or Elastic Computing Cloud? You can create virtual machines out of special Amazon machine images, so they call AMIs. Or you can use custom images as well. You can create them by your own, or you can use images which are provided by third parties. Actually, there is a market for custom AMI images, so the companies who create these images for specific purposes, they can be bought from them. If you look at the world according to Amazon, it consists of several regions, and the data transfer between these regions is ghostly, and data transfer within one region is usually free or at least very cheap. So you should decide what region your cloud service should be running at, because if you would have it running into different regions or constantly running in different regions, then the data transfer between these regions will be costly. This is actually just an example. These are some regions, there are more. For example, there's a region southeast, which is one is in Malaysia, one is in Indonesia, in Jakarta. I'm not sure about Vietnam. So there are several spread around the world. Various instance types can be used. General purpose instances, memory optimized, accelerated computing, storage optimized, and high performance computing optimized instances. So each of these, literally follows what it promises. A single instance may employ up to 192 virtual CPUs and up to 512 gigabytes of RAM. But it's depending on the instance type. So it's not all of these types will offer these limits. But as you can see, it's really it's quite a lot, right? I mean, you can actually get one instance which has like 192 processors, or virtual processors. That's really impressive. Okay. So also 512 gigabytes of RAM is really a lot. Then you also have a block device, and the block device is attached via the Elastic Block Store. These are some examples for instances. Of course, the higher the number of batches CPUs and the higher the memory, the more expensive it gets. If you want to use them, you need to follow some security considerations. So the AWS users may create a so-called access key pair, which is then used for authentication. It consists of a key and a value, basically. And you can also authenticate via a token. You also have a fine rate write management. Often it's required. And you can define the network configuration in dedicated security groups. And the instances are usually assigned an internal IP address, or it's a private IP address. But you can get a public IP address if you require it. Often you don't require it. Basically only required if you want to put a service in the public internet. But often if you want to do calculate something on a cluster, then everything should be private, right? Except of course the machine which you are using. But then again you can use a VPN to connect to it. Static IP addresses can also be acquired, but there is a premium on that. So it's called elastic IPs. But you can get a static IP address if you want. What about data persistence? So these instances, a little bit like Docker containers, they can be paused and terminated, but only termination eliminates all the running code. So be careful if you set an instance on pause, because the code will be reduced but not to zero. So as long as an instance is paused, of course, it's still blocking some resources on the AWS infrastructure, and that's why you still pay for it. So you only terminate all running codes if you terminate the instance, and if you terminate the instance, of course, if you permanently remove, everything is lost or was created or running within the instance. If you pause an instance, it does not affect the Elastic Block storage device, and the instance can later be reviewed. The termination permanently destroys an instance, including the EBS value. But you may configure that it works otherwise, so you can say, okay, I only want to destroy the instance and keep the EBS volume for whatever reason. But the default is that, of course, the associated volume is terminated as well. But EBS is expensive, so you should read and write large amounts of data to S3 storage, which is actually an order of magnitude cheaper. So very, very cheap for cloud storage. S3 is by far the cheapest cloud storage there is, at least for AWS, but also in general, I guess. EBS volume is much more expensive because EBS is actually, it's a simulated SSD, so it's really a better kind of storage. AWS offers Java APIs. It also offers command line tools to exchange the data with the S3 service. So you can either write your own program to access the data, or you can command line tool by AWS to exchange the data with S3. And that's also characteristic for most cloud services, that that's actually a business decision, that the data imported into the system is cheap, but not the export. So they always want to catch you and keep you within their walled garden, and there's no easy way out. So once you're in, they want to catch you. So they make it cheap to import data in the system, and they make it expensive to get data out of the system. So you should consider that, of course. Data transfer within the same region, within the same AWS region is mostly cheap or free. And they have a guarantee of 99.99% availability. This actually translates to 5 minutes of outage per month. So it doesn't seem a long time, right? 5 minutes per month is pretty well availability. But still, if you have a critical service, then especially when it depends if it's like 5 continuous minutes or if it's like 10-second intervals distributed across the month, it's cumulative 5 minutes. It's a difference, of course. So, and you should also be considered that AWS offers you a refund if the guaranteed availability is not achieved, but they don't refund the indirect cost caused by the outage. They only refund like if you had like 1 hour of outage, they will pay you like 1 hour operation. But that's usually not the problem. The problem is that within this 1 hour you might have lost customers who paid a lot for you. So this is of course something they won't refund you. So it's mostly in favor of AWS, of course. So this availability may not be the level of availability which is required for all of them. So you have to be aware of that. Consider, for example, you have some kind of write control system which is responding to incoming updates, and then it has 5 minutes of outage per month. So in this 5 minutes, a plane could crash or whatever, it doesn't get the calling answer. So it really depends on the application, I'd say. There are certainly applications where it's not a good idea to do this. Spot and on demand. You can have 2 types of instances, and it's actually quite nice because you can run so-called spot instances, and they are subject to arbitrary interruptions. So you have no guaranteed operation. So AWS just runs them if they have just cheap resources available, but they are very cheap. So they cost much less than the half of on-demand instances. So it's a way to actually run instances in a very cheap manner if you don't need them immediately right now, or at least not always. But of course, you can also run instances, so-called on-demand instances, which are guaranteed to be fully controlled by the users. Of course, it's more expensive. The Elastic Block Store is, from the perspective of an EC2 instance, it's just a regular Linux block device. You also must format it after creation, so it really feels like a new hard disk. And you can just format it with arbitrary file systems, and the copies of the EBS volumes can be created and also saved on S3 anytime. So no need to actually maintain EBS volume all the time. You can copy it to S3 and then terminate it. This should give you an impression of the price. So EBS costs 10 cents per gigabyte per month, so this equals 2,600 ROM for the pure storage, and 15 cents per gigabyte per month, so it would be 4,000 ROM when provided. So provided means it's available to EC2 instances. To compare it to S3, so the S3 price would be 500 ROM for data with learning access and only 100 ROM for data which are available in 12 hours. So if you can agree that the data must not immediately be available, but you tolerate at least 12 hours passing until you can access the data, then it's incredibly cheap, so for customers. So that's why you should usually go for S3, except for VM images running access and EBS values. The S3 simple storage service is organized in so-called buckets. Buckets are unique denominators, and S3 is unaware of files or directories, which you should keep in mind, because it somehow feels a little like a file system, but it's not a file system. It uses keys or objects, and these objects can be organized into prefixes, and of course, by using prefix filters, you can simulate something like a directory structure, but it's not a directory structure in the narrow sense. So technically, it's not a file system. It's basically just a key value store, and an unlimited number of objects can be stored. Every object requires 2 kilobytes for metadata. So be aware of this. If you want to store many very small files, then of course you have a problem. You should somehow compress them or pack them together and then store this as one single file. Otherwise you will have this overhead. The maximum object size in S3 is 5 terabytes, and it's accessible via a web interface or APIs. There are REST APIs. There's also a Java wrapper for this, but basically the Java classes internally also use the REST interface. And you also have a command line tool to access S3, so you can use this command line tool, for example, to synchronize the local folder with an S3 folder. There are 2 durability levels which are offered. The standard storage level, which is 99.999999999% durability, which is mostly enough. But there's also a reduced redundancy durability level, which is only 99.99% durability, which of course means that 0.01% of all data may get lost within 1 year. So you may say, okay, that's not so much, right? But consider that in case you would, for example, store binaries or executables on the storage, then even one single byte flip would make it defective. So it really depends on the kind of data. Of course, there are data types which are robust, so you don't need to care about single bit splitting, but in general, if you have the appropriate data, it may be a problem. It's also offline import via hard drive shipping is possible. It's called AWS Snowball. So it's an interesting concept. So you basically will just ship them a hard drive, and then they manually transfer the contents of the hard drive onto S3. So it's a very long ping, right? So it's a very long latency because of the postal service. So, I mean, it depends on the postal service. I mean, fast postal service, but still the ping is not good. But actually the transfer rate can be quite high, because if your hard disk is very big, then you can transfer lots of terabytes at once. Can be faster actually than transferring it via any network, because you can not only import a single hard drive, but you can just give them a bunch of hard drives and tell them now to import it into S3. The largest competitor of this service is Google Cloud Storage. Google Cloud Storage also offers a limited S3 compatibility. So you can see that actually S3 is more like the dominating the market. That's why actually Google offers adoption on the interface of AWS. Usually Google is not forced to actually support someone else's interfaces, but in this case they do. So you can see that S3 is actually number 1 in the market. I don't know about the prices of Google Cloud Storage, but I guess they will work similar. What about the Elastic NetReview service? As you can see in this diagram, we have this EMR service, and this is actually an advertising image from AWS. It's why it can easily run and scale at Spark, HiveQuest, and other data workloads. So it may not be as easy as they promised, but at least you can do it, as I say, so you can write the state and then Spark. Then you choose your open source data framework. And basically we have this EC2 for the virtual machines. We have possibly also Kubernetes containers in this Apache EKS. And you can also add on-premise hardware if you want, and services called AWS Outposts. And you could also have AWS Lambda services. And everything is orchestrated by EMR. So basically EMR is some kind of umbrella for all these lower services which are being orchestrated. That's why there is also a premium on EMR. So you have to pay if you're actually using EMR to steer, to control EC2 instances. You will not only pay for the EC2 instances, but also something for EMR itself. So it's a cluster platform for the operation of the data frameworks, such as Hadoop and Spark. It offers automatic provisioning and running of uniform EC2 instances, which are then set up with a defined software stack. So you can, for example, say you want Spark as a software stack. And where there's a management console, which you can use to monitor and control the entire cluster. For example, for Spark, there's a management console called Spark UI. I will go into detail on this later. So this would be a typical EMR workflow. This is also imaged by Anderson, but I guess shows the basic concept. So you start with planning the storage, choosing the appropriate framework. Then you develop the app, you test the app locally. You may select different hardware or networking, also security. Then you launch the cluster on the EMR console. Once the cluster is up and running, you connect to the cluster. And then you can submit actual work to the cluster. Well, this little line here means that the cluster is pretty much fixed. Then you have finally results, you can view them, you can monitor the cluster, and you can also troubleshoot on the problems and scale up. So often you would first let the cluster work on a small percentage of the data, and if everything works as planned, then you will scale it up until you have reached the level you want to reach. And finally, of course, you terminate the cluster and delete all the resources, because I wonder why it's in here, because AWS makes more profit if you don't do this. But as I said, be careful. If you don't terminate a cluster, it will just continue running, and the cluster costs like 20 euros per hour, which can happen. That's a lot of money, depending on how long it takes to realize that. Also, it's not easy to actually control, put a cap on the cost of AWS. They make it very difficult to actually set a limit for the cost. I guess it's intentional. You can actually use EMR interactively. So you run an EMR cluster with a predefined software stack and custom software, which, for example, works on top of Spark. But EMR deploys this software to every node. Then you connect to the master node. You can use this, for example, with PuTTY. Probably most of you know PuTTY, so it's a terminal software. Then you can start cluster workloads, for example, with the tool Spark Site, which we will also later display in detail. And the data are usually retrieved from an S3 storage. You can then monitor the execution, for example, with the Spark UI console, or just looking at the log files. And finally, terminate the entire cluster, also via the EMR console. And all of this can be automated, of course, via start and termination scripts. So that would be like a regular way of using EMR. And this is an example of EMR cluster creation. Okay, so this is a screenshot of the Java console that I guess indicate the area. So here, as I showed already, so you can set a location for the log file, you can select the software set, select the hardware configuration, and also you set the security access levels, and then you can run your cluster. If you look at the prices, as I said, EMR comes with a premium, and you also need to pay, so it's really like, many small costs together can go big as well, so be careful, because you not only pay for EC2, you also not only pay for EMR, but you also pay for S3, and you also pay for data communication. So if S3, for example, gets its data from something you have on premise, then you will pay for this incoming traffic as well. As I said, if it's outgoing traffic, you will pay much more for this as well. So be aware that they are charging for many things you might not be aware of immediately, especially network traffic. So network traffic is charged as well. So if you have an application which creates lots of I/O, then of course this will also generate substantial costs. Here you can see some prices in US dollar for a general purpose EC2 instance in Frankfurt. So the prices vary depending on the region. Because, for example, if you want to have something running in Germany energy is very expensive, so it's like more expensive to run in Germany than in the US, for example. So you can see here, this would be like 27 cents per hour for an oil X large. Then we would have an additional about 6 cents per hour for the EMR service. And for this you will get 4 virtual CPUs, 16 gigs of memory, and up to 12 gigabit of network performance. And at the bottom here you can see, okay, if we pay like $3 per hour, I guess $1 is roughly 30,000 drums, so it would be like 90,000 drums. So 100,000 per hour. So then you would have 70 cents in addition for the EMR service, but you would get 48 virtual CPUs, 192 gigabytes of memory, and about 19 gigabits network. So just to give you an estimate about the prices for this service. So it depends on what you want to do, because consider that this is per instance. So I mean, a cluster usually makes not much sense if you have just one instance, right? So because then you would just run one EC2 instance in EMR. So usually I'm using this like, for example, 16 or 32 or 64 instances to set up a large cluster. And now if you consider like you would pay $3 per hour for one instance here, then if it's 10 instances, would be $30 per hour, of course. So you now calculate what this would cost you in a month. So it makes sense to only fire this up when you actually need to run it and then terminate it. But of course, if you use like 30 machines instead of 3, then it will be roughly 10 times faster. So it may make a lot of sense to actually even pay lots of money to make it work very fast. Because then you get your result very fast, and also our working time is also paid. So time is money. So it's actually can be a good business decision to do. What is AWS Lambda? As I said, it's a function as a service platform. It's serverless, it's event-driven, and the code is always run as a reaction to events. So you always define trigger conditions, so-called events, which then cause the execution of the code. All the resources for the execution are managed automatically, and technically what we have here are Linux AMI containers. So behind the scenes it's Linux AMI containers, but we don't see them, we don't have direct access to them. It's supported, it supports Node.js, Python, Java, Go, Ruby, and also C#. And applications are always implemented as microservices. This is a minimum example of a Lambda function for Node.js. And as you can see here, we define a handler which gets this tuple of data, so we get an event and the context. And this always has the format of JSON. For example, here this would be our event JSON. This time this is just a function that calculates the area of two given parameters, length and width. So very simple. And yeah, what we are doing here is first we are getting these properties of our event base. Then we are calling a function which we have defined here, which basically just calculates the area. And then we are logging it, so the result of the function. And then we are defining our result JSON, which is again JSON. So input is JSON, output is also JSON. So finally, we run the JSON converted version of our data, and the output would be something like this. So the response would also be JSON, in this case, the calculated area. And at the same time, you could see like this log file. So you can see you can log to the console here, and you can get information which the log group is actually being executed. And you also get some status report, like how long your function took to execute, you get the duration here, also the build duration, because actually it's built by execution time, so in the millisecond exact, so every millisecond they will charge you. So this time this call was 21 milliseconds of execution time, so 21 milliseconds of execution will be charged. Also the memory available and the maximum number of memory use is given here. This is also, the more memory you use, the more expensive a function becomes. That's why it's also printed here. So these are the most important aspects for estimating the cost. Yeah, and also the entire duration of the initialization is given. Okay, so you see a quite basic example how this works. And it's really not complicated, right? So you can just write a microservice right away using this kind of pattern. The costs for Lambda are created by requests. So you pay about 20 cents, and these are euro cents, I guess, but euro and dollar is roughly 1 to 1 currently, I guess. So 20 cents per 1 million requests. The execution time depends on the allocated memory. So if you have 128 megabytes of memory, it's 0.8 cents per hour, but if you have 10 gigabytes of memory, it becomes 60 cents per hour. So you can see it's like non-linearly increasing, right? So they want you to have as few memory as possible. Of course, memory is expensive. You also have data transfer costs, which you pay separately, and you may also have further costs. For example, you can request that the code shall be executed close to the user. In this case, you will have some control about the physical location where the code is being executed, but of course, added premium. Yeah, as I said, it looks fair at first, but of course you have to be careful that there are some drawbacks, and it's hard to get an application out of this. So what are the advantages? You have no server management, the costs are roughly proportional to the research usage, you have no step costs, it's also important, right? So you can scale up as needed. So if, for example, you have run a small business and then you have a search on demand, you can scale up and then it just will work flawlessly. No step costs involved. You can also scale down again if the application is not required so much anymore. It's scalable with little or even no effort on the user side. You don't need to tell AWS that you need to scale up the demand. It's also fast. You can very quickly deploy updates. And yeah, you also have a fast implementation of services due to the simple deployment process. But as I said, it's a vendor lock-in. It's difficult to debug and test. It's potentially susceptible to vulnerabilities. And also the abstraction of the hardware comes with it. Okay, so to sum this up, AWS offers especially two services. As I said, in German, of course, offer hundreds of services, but yeah, especially two services which enable the manage, control, and usage of a large number of resources. And the first one is EMR. This is used for the management of clusters, consisting of virtual machines on the EC2 service, which use EBS volumes as block devices and S3 buckets for large amounts of application data. You can alternatively also use Kubernetes containers. And Lambda, which is a function as a service platform for event-driven serverless implementation of applications, which automatically scales resources. And these services are controlled either via web console or via REST interface, or via a command line tool, which is, by the way, also only using the REST interface, or via a Java API, which is also using the REST interface. So basically everything is just using the web interface. Also the web console is using the REST interface. Right? So basically everything is REST for them. The costs are roughly proportional to the resource usage, especially with respect to the memory, the CPU, the data transfer, and the storage. And for Lambda, also the I/O load is built. And yeah, S3 is suitable for the very cost-efficient storage of very large amounts of data. Okay, so that's it. Then I'd say we have 50 minutes of pause break. And then